Okay, for problem 7-9 here, we have a question about how many books people read. Okay, so the magazine is making a claim that the people read an average of more than 2 books in a month. A survey of 20 random individuals found that the mean number of books that they read was 2.2 with a standard deviation of 1.3. So to test the magazine's claim, what should the appropriate hypothesis be? Okay, so it's creating an hypothesis that it's going to run against. Okay, so it creates almost a straw man hypothesis, null hypothesis here, that the books read, and that's mean, we're going to do mean here. Okay, so the mean is less than or equal to 2, and its hypothesis, either H1 or HA, okay, is that the population mean is greater than 2. So we know that we watch on hypothesis, alternate hypothesis, we look for the sign here and it's pointing to the right. So we know that this is going to be a right hand test. Okay. We have fewer than 30 sample readings. Sample count's less than 30. We also only have the standard deviation of the sample, not of the population. So we create a straw man argument of 2 books. Okay. And we're claiming that it's less than that. So it's almost as though it's a reverse situation here where we create the straw man from our hypothesis. Okay, and this is much more akin to what happens in industry out here, right, or science or whatever else. Is you create the hypothesis and you run it against a straw man is what you're really doing here. Okay, so I want to drop in some of the interesting parts to this. I'm going to create a little key here of the key data. So we are going to end up with T critical, not Z critical here. T critical, we'll figure that out. If I could spell it. We're going to need the test statistic, which for this problem is going to be using the T distribution. And then finally, we're going to figure out what the p-value is, right? Let's see, now we're using the T distribution. So what is a T critical? Okay, so similar to what we just did, like Z critical, here we need to use the formula, the T distribution dot inverse of a certain probability. But if you read the book, you'll understand that we need to take 1 minus alpha. Okay, we compute it to the right. Okay, so we need to go to the right side of the zero centered T distribution. And different than the Z crit value, we also have to put in the number of the sample size minus 1. Okay, so it's a little bit different. Okay. So we end up with a T-crit of 1.7293. Okay, where does that end up? Over here on our drawing. Okay, I'm going to redraw it because that was the native units up above, and I just want to show this is the T distribution. Okay, and the T distribution gets flatter and wider the fewer the number of sample points you have. How many sample size is, okay? But it's still zero. It's zero. This is zero centered, like the Z is. This is our native units, just to keep it different, native units. Okay. And so our T stat is here. It says that 1.72913. Okay. So what's going to happen here is we're going to run our test statistic using the T. Okay, using T, it's calculated almost the same as the Z. For the Z case, we do the test statistic is almost the same thing, but here we're going to use the sample standard deviation. It's the only difference between this and when we do it in the Z distribution world. Okay, so what we're going to look at a priori here is our alpha. Okay, so our alpha of 0.05 is an area or a probability here. Okay, so that's alpha moving this direction, moving to the right. It's the area to the right of the T statistic, or the T critical, all right? Okay, so if we find a point, if we find by running this on our sample data that we end up just change the color here. That was a fat pen. Some of these are fat. If we end up where the test statistic is greater than T critical, or that it's the same thing, these are just computed from each other, or the area, if the P value is less than alpha, see, it's the same thing. It's just flipping a reference. It's all it is. We're just describing the same thing, or we're either using the actual value of T's here, or we're using the associated probabilities of them. See, so it's an issue of language or reference here in industry. Okay, so this problem is quite realistic here. So let's do the T-stat. So that's going to be equal to sample mean minus the implied population mean divided by, and here we're going to use the sample standard deviation over square root of n. Okay, so notice you can already see what's happening here. Our test statistic didn't make it. Okay, so it's inside here. So let's call this is 1.7. Let's call this 1. Okay, and so we're down at 0.72. We're down at 0.72, like right maybe here, something like that. So clearly we didn't break through the threshold. We didn't get more extreme. So the p-value is equal to 1 minus, for the right side, we need to subtract it from 1. 1 minus t dot dist. First argument is our computed test statistic. Second argument is sample size minus 1. Finally, we want cumulative computation. Put that in there. And we ended up with 0.2379. Okay, so what we did is we already saw that we so to speak, we failed to reject. Okay, so here we could not reject the null hypothesis. Okay, we just didn't have the type of information here that involved the variability, the S, or the standard deviation of the test. We didn't have enough sample types of enough samples. So the sample size was not large enough to meet the criteria. Okay, so it kind of fails on two different things. All right, but anyway, what ends up happening, these two tests, using our test statistic, we do the same thing that we do with our p-value, and this is sort of a transitional conversation to get us thinking about this alternate framework that we use. You know, the rejection area, the rejection zone versus the size of these two areas. Okay, and so just to finish this off, I'm going to put this over here as text, and I'm going to put this over here as text, which shows the equations that we use to get those computations. All right, I'll run this one as well. And there you go. Okay, so now you're set up for doing two different kinds of z's. Okay, so you could run z whether you're doing the upper or lower tail, either the upper or the lower tail. Okay, so this would be where your H naught says that your spec, something that you're looking at, right, is greater than a constant. Okay, and this is where your, make that HA. Okay, so your alternate, or HA or H1, is the here you put colon, and your spec is less than a certain constant. So we know from 7.7 how to do those two types of problems. From here we know how to do the upper tail on a t statistic, because two things: we had fewer than 30, the sample size of fewer than 30. We also had the standard deviation of the test of the sample itself, not of the population. All right. So we did Z and T. So you can get the idea of how you would handle the opposite in each of these. Okay, so you have a matrix, a matrix built that says what? Here we could have less than 30 sample size here, greater than sample 30. sample size, and standard deviation of the population given or not. Okay, so that's the standard deviation of the sample. Okay, so this is the matrix that you have, a 2 by 2 matrix. When do you use each of these things? Okay. Now the fifth, you'd actually call the fifth falls into play when the hypothesis is that the null hypothesis is that, put a colon there, is that the parameter you're looking at is equal to some constant, and your alternative is that mu is either less than k or k is it's greater than k. And that's the two-tailed test. And pretty much all you need to do is divide alpha over 2 because you need to spread the alpha. Remember, alpha is a probability. You need to spread it equally in the low and high tail. So that's basically how you handle all these problems. And the quicker you, more of these do, more of these you do, the faster you get going on them. So hopefully this was helpful. Gives you some shortcuts and insights into how exactly you calculate this thing. The trick or the thing to keep in mind is it's the same test, only it's a language. It's like specifying it in French versus German or something like that. It's the very same thing whether we specify it by whether we exceeded the threshold with the computed test statistic or whether we take it one step further and we just look at what the p-value is. And you have to remember how the p-values are relating to the test statistic. Okay, is the area less than or greater than the area of the alpha? Okay, that's the best way to remember it.